ever get that feeling, you're stressed and the same thought just keeps like bouncing around in your head?
Yeah.
Like a broken record.
Yeah.
Turns out you can actually create a sound effect that kind of mimics that.
It's wild.
You sent us this research paper about it. Some pretty wild stuff they're doing with sound.
It is really interesting, yeah. The way they're using digital signal processing, DSP as it's called.
DSP, right?
Yeah, to recreate those sorts of psychological experiences through sound.
It's like taking this abstract feeling, the stress, and making it into something you can actually hear.
Absolutely, yeah.
So how does it actually work, this stress effect?
Well, so imagine, a sound wave.
Okay.
Right? Think of it like a ripple in a pond, right? It's smooth, it's going out, and what they're doing is essentially they're creating controlled echoes and delays within that sound wave.
Gotcha.
To mimic that feeling of repetition and tension that we associate with stress.
So instead of a smooth ripple, it's more like that ripple keeps hitting a wall.
Yes.
And bouncing back, and you get this jumbled, overlapping effect.
That's it. They're using what they call a stress generator, which is basically a set of mathematical instructions that tells a computer chip how to manipulate those sound waves. So it's almost like giving the computer a recipe for stress.
A recipe for stress. I like that.
But instead of flour and sugar, it's echoes and delays.
Right. Yeah.
Exactly.
But it's not just about recreating stress, though.
No.
This paper goes into a bunch of other cool audio effects as well.
Yeah.
One that I thought was really neat was this multi-echo thing.
Yeah, the multi-echo effect.
Yeah.
That's all about creating that illusion of sound bouncing around in a space. So imagine, you're in a cathedral.
Okay.
And you clap your hands. The sound doesn't just disappear, right?
Right.
It kind of echoes. It reverberates.
Yeah.
It creates this sense of depth and grandeur.
Totally.
And that's what they're doing with multi-echo.
So like those epic movie scenes where, the character yells in a huge hall. And the sound just seems to go on forever.
Exactly. And what's cool is they can control the number of echoes, how far apart they are, how quickly they fade away.
Wow.
So they can make it sound like a small room or a giant cavern.
Oh, wow.
Just with a few tweaks.
That's wild.
Code.
So they're giving sound engineers this, digital toolbox to create these immersive sonic landscapes.
Yeah.
And speaking of sonic landscapes, they also talk about making a single voice sound like a full-blown choir.
Right.
With this reverberated chorus effect?
Yes.
How does that even work?
Well, so it's combining two key elements, right? You got natural reverberation, which we just talked about.
Okay.
That cathedral effect.
Right.
And then what's called a chorus filter. And the chorus filter basically creates multiple copies of the original sound.
Okay.
But they're slightly detuned from each other, right?
Okay.
So they're just a little bit different.
Gotcha.
And that's what makes it sound thicker and richer, like multiple voices singing in unison.
So they're taking one voice, making it echo like it's in this big space.
Yeah.
And they're layering those echoes on top of each other.
Exactly.
To create that choir effect.
It's like audio alchemy. It's taking something very simple and making it much grander and more complex.
It really is. It's mind-blowing how they can use math and code to do that.
Right.
To create these illusions.
It was amazing.
With sound. But they didn't just stop at creating the effects, right? They actually built them.
They did, yeah.
They used this thing called a TMS 312C6713 DSK.
It's a mouthful.
It is a mouthful. What even is that?
So think of that like a tiny specialized computer chip.
Okay.
Designed specifically for processing audio. So that's what allowed them to take those theoretical calculations and translate them into real world sound.
So it's like the bridge between the digital world of ones and zeros.
Exactly.
And the physical world of sound waves that we hear.
You got it. And they used a program called Simulink to kind of talk to this chip.
Okay.
And tell it exactly how to manipulate the sound waves to create those effects that we've been discussing.
So Simulink, this is like a pretty powerful tool.
It is, yeah.
I imagine it takes some serious coding skills to use something like that.
You might be surprised, actually. While it is based on complex math, Simulink is actually designed to be relatively user-friendly.
Oh, wow.
And they even, compared it to traditional programming methods. And we'll get into that.
So Simulink, like this digital audio toolbox, but it's surprisingly accessible.
Yeah, that's the idea.
Yeah, even if you're not like a coding master.
Right, exactly.
But you mentioned they compared it to traditional programming.
Yes.
What did they find? How'd that work out?
Well, they discovered basically that Simulink could be a real game changer for audio engineers. Basically, their research suggests it could cut down the time and effort needed to develop these effects, like, drastically.
Okay, so instead of taking, like, a year to make something, it might take a month.
Potentially, yeah. I mean, imagine being able to create a complex soundscape in, a fraction of the time it used to take.
Yeah.
That's the potential here.
Yeah. And that's huge, not just for the engineers, but that's got to trickle down to listeners too.
Totally.
Right? Like, if it's cheaper and faster to develop these crazy audio effects, we should see more affordable, better listening experiences for everyone.
For sure, for sure. I mean, think about the possibilities just in, like, video games, for instance.
Right.
Imagine a world where the music isn't just a static soundtrack, right? It's like it adapts in real time to your actions, to your choices.
Oh, wow.
And because Simulink makes the development more efficient, these sorts of features could become standard even in, like, smaller indie games.
Right.
Not just these big budget titles.
Yeah, so it's like a whole new level of storytelling, but through sound.
Exactly, exactly.
That's so cool. And you mentioned that they actually tested how Simulink stacked up against traditional programming.
Yeah.
Like, how do you even go about measuring something like that?
So they use something called the constructive cost model, or COCOMO.
What?
Yeah, it's kind of a mouthful.
It is.
But it's basically a way to estimate how much effort, how many resources a software development project will require. So think of it like a cost estimator for, like, building a house.
Right.
But instead of bricks and mortar, it's lines of code and algorithms.
So they basically ran the numbers, right?
They did.
To see, like, okay, how does Simulink measure up?
Yeah, and their analysis showed that using Simulink could reduce the workload of these audio projects by, get this, up to 10 times.
10.
That's huge.
That is huge.
And then the development time, they said, slashed by up to 5.5 times.
Wow. So we're talking finishing projects in weeks that used to take
months, potentially, yeah.
That's wild.
Yeah.
But it's not just about saving time and money. It's about making this technology accessible to more people.
Totally.
And hopefully that'll lead to more innovation in the audio space.
Absolutely, yeah. A wider range of creators, new ideas.
Totally.
Yeah, it's exciting.
Yeah, that's really cool. And it's not just Simulink that makes this research really interesting.
Right.
They also dig into, like, the really technical stuff.
Yeah.
About how these effects are processed in real time.
Yeah.
Because that's the thing.
Exactly.
We've got to be able to actually hear them, right?
It's gotta work.
Like that stress generator that we talked about.
Yeah.
Needs to be able to, like, I don't know, manage all those calculations on the fly.
Right.
Without, like, the sound cutting out or lagging.
Right, because a stress effect that keeps, like, glitching wouldn't be very effective.
Right.
Yeah, you're right.
So what'd they find there?
So that's where these scheduling techniques come in, right?
The scheduling.
Yeah, think of it like like a chef.
Okay.
Managing a really busy kitchen, right?
Okay.
During, like, the dinner rush.
Gotcha.
They need to make sure that every dish is prepared correctly.
Right.
Served on time.
Yeah.
You don't want anything to get, like, burned or overlooked.
Right.
So in this case, right, the dishes are the different audio effects being applied.
Gotcha.
And the chef is that DSP chip we talked about.
Okay, so, like, walk me through these scheduling techniques.
Okay, sure.
Which one is, like, I don't know, the Michelin star chef of audio processing?
Okay, yeah, so they focus mainly on two main techniques: idle task scheduling and DSP BIOS task scheduling, which is another mouthful.
It is, yeah.
But the idle task scheduling, that's kind of like, that chef prepping ingredients whenever there's a lull in orders.
Okay.
So it's like, it gets the job done.
Right.
But, it could lead to delays if, like, a sudden rush hits.
Right, so that's not ideal for music.
Not ideal for real.
Where you need everything to be on beat.
Yeah, exactly.
So what about that second one? What was that, DSP?
DSP BIOS, yeah, this one's much better for that.
Okay.
That's like having, not just one chef, but a whole team of, like, sous chefs.
Okay.
Each one dedicated to specific tasks.
Gotcha.
This way you guarantee those really crucial audio effects get top priority. And they're processed without, any delays or glitches, no matter how much else is going on.
Yeah.
So it's much smoother.
Gotcha.
And the researchers actually found that DSP BIOS consistently delivered, like, the cleanest, most reliable audio output.
So it's like the difference between seeing a live concert.
Yes.
And everything's just like flowing.
Exactly.
And the music's perfect. And then seeing one where it's like music keeps stuttering and skipping.
Exactly. You want that seamless, uninterrupted.
Totally. But before we get too deep into the weeds here.
Yeah, for
with
sure.
all the technical stuff, let's bring it back to what actually matters, which is the sound.
Right.
So we talked about stress and echoes and choirs. What other crazy sounds did they create?
So many.
They also created that like classic concert hall sound.
Yeah, the reverberation.
Yeah.
It's really about recreating that way that the sound kind of lingers in the air,
Right.
Bouncing off the walls.
Yeah.
Creates this like really rich, immersive atmosphere.
Like you're listening to a live recording and you can almost picture the space.
Exactly.
Around the musicians.
Yeah, and they achieve this using a really clever combination of digital filters.
Okay.
Think of them like almost like virtual sound mirrors.
Yeah.
So one of these filters is called an IIR comb filter. And what that does is it creates a series of echoes, right?
Yeah.
But they're timed very precisely to mimic the way that sound would actually bounce off the surfaces in that space. And then they use another filter on top of that called an all-pass reverberator that smooths out the echoes, gives them that natural decay.
Oh, okay. So it's like the first filter, the comb filter is like...
It creates the initial bounce.
Yeah.
And then the reverberator kind of adds that final touch of realism.
Yeah. Very cool. And they did all of this on that, what was it called?
The DSP chip.
The DSP chip,
Yeah.
Which is, again, speaks to how accessible this is.
Totally.
It's not just about creating these wild sounds, but making it so more people can use them.
Absolutely. It really makes you wonder, like, where do we go from here?
Yeah.
This research was on pre-programmed effects, but like, what if we could make them responsive?
Okay, now you're talking. Like, what do you mean? Like, effects that change based on the music?
Yeah, or even how the listener is feeling.
Oh, wow.
Imagine like a movie score that changes based on your heart rate.
Oh, that'd be creepy.
Or like a video game.
Yeah.
Where the sound effects totally change as you go through different places.
That's wild.
We could even have like personalized music that adapts to your mood.
So we're talking like AI.
Exactly.
Taking all this stuff we talked about and like...
giving it that extra dimension.
Giving it a brain.
We're not that far off, actually.
Right.
With, AI and machine learning, we're already seeing systems that can analyze complex data.
Right.
Including music and biofeedback.
Yep.
It's not hard to imagine using that to create these real-time audio experiences.
So the future of sound design is, it's going to be interesting.
Yeah. It's going to be wild. Sound isn't just something we hear. It'll be something that interacts with us.
Responds to us.
Yeah. Anticipates our emotions.
That's wild.
It's pretty amazing.
It really is. Well, this has been an incredible deep dive.
It has.
We went from like the super technical stuff about digital signal processing to... I don't know, the future of sound.
Yeah, it's crazy what they're doing, right?
It really is. It really highlights how, like, even a really focused research topic can have these really unexpected applications.
For sure. And it all started with the idea of, recreating stress with sound.
It's wild. It's like we're just starting to understand how to, I don't know.
Yeah.
Speak the language of sound,
Totally.
Well, to our listeners, thank you for joining us on this sonic adventure.
It's been fun.
We hope you've learned something about sound design.
Yeah.
And how it might shape the future.
Absolutely.
Until next time, keep those ears open.
Yeah, stay curious.
And your minds open to the possibilities of sound.